This is Math 139, Section 3.4, where we'll be talking about the composition of functions. Composition is basically a way of combining the actions of two functions into one single function. As an example, I'm going to start with the two functions f of x, equaling x plus 4, and g of x, which equals x squared. We'll start by concentrating on the f. I've got specific inputs for my f, and then I'm going to put the outputs over here. So if I put 1 into my function f, 1 plus 4 would give me 5. Plugging in 2, 2 plus 4 would be 6. And plugging in 3, 3 plus 4 would be 7. Okay. All right, these are definitely outputs for f, but I'm now going to use these outputs as the inputs into the g function. So if I plug 5 in for x here in the g function, I would get 5 squared, or 25. Plugging in 6, 6 squared is 36. And finally plugging in 7, 7 squared gives me 49. So we've got this sort of sequential thing going. Into f, out of f into g, and finally out of g. The composition of f and g is simply the one function that represents both of these actions at the same time. So if I first do f, that is, take the x and add 4, and then I do the g and square that entire result, I can call that a new function h of x, which we'll describe in just a minute as the composition of f and g. Just to test it out, it should go from here all the way to the output in one step. So if I were to plug in 1 plus 4 squared would be 5 squared, or 25. And again, you can see we've gone from the initial input to the final output, all with one function. Same thing with the 2. Plugging 2 into this function makes that 6 squared, or 36. Again, from the initial input of 2 all the way to the final output of 36 with one function. And lastly, plugging in 3, 3 plus 4 squared would be 7 squared, or 49. From the original input all the way to the final output in one step. So this is the idea behind our compositions. Let's put a little bit of notation into this. If we define this function h of x as the composition of f and g, we write it this way. H of x is equal to f composed with g. So that little open circle there is read composed with. What it really means is the way I've got it written this way. We would do g of x first, and then follow it with f. Actually, that's backwards from what we did. We really did g composed with f, because we did f first. So let's write that one out as well. G composed with f of x would be g of f of x. And that's actually the one that we have, because we did indeed do f first and then g. All right, we're going to practice finding compositions for a couple of different examples. In this next example, I've got the function f of x defined as 3x plus 1, and g of x is 2x plus 6. Let's go ahead and algebraically find the compositions. F composed with g of x, and then also g composed with f of x. I'll start with f composed with g. That means take f of g of x. So we're doing g first here. But I know how to do g of x. I take 2x plus 6. So I'm going to actually replace that g of x with the 2x plus 6. Just plug in what g of x is equal to. Now I have to take this 2x plus 6 and use it as the input for the f function. So plug it in for x up here. I'll get 3 times, and instead of x, I put in 2x plus 6, and then the minus 1. We'll simplify that a little bit, and that'll be it. Distributing the 3, I get 6x plus 18 minus 1. And combining like terms, 6x plus 17. So there's the composition, f composed with g of x, or sometimes just f of g of x. I now want to ask the question, is it going to matter if I reverse the order of the composition, g composed with f of x? Mathematically, we get that fancy word, is composition commutative? Can you reverse the order without changing the answer? You all know that sometimes that works with certain mathematical functions and sometimes it doesn't, right? We know that we could add or multiply and we'll get the same answer no matter what order we write those operations in. But we do get a different answer for example, subtraction or division if we change the order. So we're asking now, is this one commutative? Will I get the same answer? Or is it not commutative? Will I get a different answer? Let's check it out. This would be g of f of x. So this time I'm doing the f first. I'll take that f of x and replace it with what f equals. 3x minus 1. And now I want to take g of 3x minus 1. So I'll go over to my g function and I'll replace that x with 3x minus 1. So 2 times 3x minus 1 plus 6. Again, we'll just kind of do a little bit of algebra to simplify. I'll distribute the 2 first and then just combine my like terms. 6x plus 4. And you'll, of course, notice right away that we definitely got a different answer when I reversed the order. So we can kind of draw the conclusion here that composition is not commutative. That is, changing the order changes the answer. All right, let's practice taking a composition algebraically one more time. I've got 2 new functions for f and g, and I'm going to do f composed with g of x first. So that's f of g of x, or f of x plus 2. I plug the x plus 2 in for the x's in f, and I have x plus 2 squared plus 3 times x plus 2. X plus 2 squared, remember, is really x plus 2 times itself. So that would be x squared plus 2x plus 2x plus 4. And then distributing the 3 plus 3x plus 6. And putting all my pieces together, I have x squared. Let's see, we've got 2, 4 plus 3 would be 7x's. Plus the 4 and the 6 would make a plus 10. So there's the composition f of g of x. Let's check it out the other way. G of f of x. Really means g, literally, of f of x. Or g of x squared plus 3x. I now go to my g function, and I replace that x with x squared plus 3x. And then g just says add 2 to that. Since there are no like terms, that's simply done. Once again, we see we definitely get different answers, so we're definitely not commutative when we're looking at composition. All right, one last thing with composition. We've looked at the algebraic process for finding compositions, but we can also look at a graphical process for taking compositions. I have here two graphs, an F and a G, and just to make it a little bit easier to talk about them, I'm going to color code them here. Let's let F be the parabola. And we'll let G be the linear. I would like to find compositions for specific values of x based on these two graphs. And I think I'm going to make this just a little smaller so we can see the graph and the chart in the same picture. There we go. All right. First of all, I'm defining h of x as f composed with g of x, or f of g of x. If I'm going to plug in 0 for my x value, I would have f of g of 0. Now, g of 0 I can read right off the graph. That would be f of what? Well, let's see. G was the orange line here. So g of 0 right here is 3. I now want to take f of 3. F is the pink, the parabola. So let's see, 1, 2, 3. F of 3 right here. Looks like it's going to be 7 for that y value. So f of g of 0 is 7. Let's do a couple more. F of g of 4. I start with the g of 4. Again, g is the orange, the line. So here at x equal 4, right there, the y value would be 1. Now I want f of 1. F is the parabola, the pink. So I come over here to x equal 1. And on the parabola, it looks like that y value is down here at negative 1. All right. One more in this direction. Plugging in 6, I'd have f of g of 6. G, the orange, is the line here. And at x equals 6, the y value right there is 0. So that would be f of 0. When x is 0, coming down here to the parabola, it looks like the y value is negative 8. So that's how we can kind of read compositions right off of graphs. Let's go the other way. K of x is g of f of x, which I can write like this. So notice this time I'm going to be doing the f first, and then the g. And once again, I'm going to start with 0. G of f of 0 would be g of, let's see, f of 0 is our negative 8. Oh boy, and I'm in trouble now. I don't have enough graph to do this. I could, of course, extend the linear graph if I had enough space and do this, but I'm just going to go ahead and say we're now off the graph, since I kind of messed up and didn't give you a big enough graph to see that on. Sorry. Let's try the next one. Plugging in 4, g of f of 4. So let's see. F of 4. When x is 4, it looks like the y value right here is 8. Looks like I did give us enough space on the positive 8 here. If I come over to 6, 7, 8 for x, come down to the orange graph, looks like our y is negative 1. And finally, plugging in 6, I'd have g of f of 6. See, f of 6. For here at 6, on the f graph, looks like the y value is 4. And g of 4, when x is 4, right here, it looks like g is 1. So there's my compositions read off graphs. And that's the end of section 3.4.